Hello everyone. Welcome to the ILTA Physics Online lecture. Today we are going to study free fall, which is a type of one-dimensional motion. Free fall is a one-dimensional constant acceleration motion caused by the force of gravity, which pulls objects toward Earth. Here I mentioned gravity, and this physical quantity force is actually a very important key factor that we will study in the next chapter. So in a way, this is like a spoiler or a preview of what is coming next. Now, the main difference between free fall motion and the one-dimensional constant acceleration motion we studied before is that the motion here happens vertically. So actually, there is nothing completely new here. You just take everything you already know about constant acceleration in one dimension and apply it vertically. Stand your thinking upright. That kind of sounds like a philosophical phrase, doesn't it? Another thing to keep in mind is that the direction of motion can change. Earlier, we said that when motion gets a little more complicated because the direction changes, we can analyze it by breaking it down into small intervals where the direction stays the same. The same idea can apply here to free fall motion. For example, when you throw a ball upward, at first it moves upward, but then at some point it stops and starts moving back downward. This kind of motion is the most typical example of free fall. So in this case, we can clearly see that the direction of motion changes from upward to downward. We will look at this kind of free fall motion by dividing it into two intervals, and also see how we can express it with a single equation. I might have gone into a bit of a long explanation right on the first page, but when you are studying, it is really important to have the big picture in mind, and then carefully study each part in detail. Alright then, with this big picture in our heads, let's start by understanding free fall motion. After that, we will review the general problem-solving process for one-dimensional constant acceleration motion, and then wrap up today's lecture with a simple example problem. Like I said earlier, free fall is really just a special case of the one-dimensional constant acceleration motion we have already studied. So before we move on, let's take some time to carefully review what we have learned so far. In our last lecture, we studied constant acceleration motion. And when I say we studied it, I mean that we looked at it in two different ways. First, graphically, using motion graphs, and second, mathematically, using the kinematic equations to calculate velocity, displacement, and position. The type of motion we studied was horizontal constant acceleration. The direction of motion did not change, it stayed the same, but the speed changed steadily, with acceleration remaining constant. This was the simplest kind of accelerated motion. You can imagine a motion diagram for this case. The object moves from left to right, and as it moves, its velocity increases. But the rate at which velocity increases, that is, the acceleration, remains constant. By now, you should be very comfortable reading motion diagrams like this. When you see one, you should be able to tell right away what kind of motion is happening. We can also represent this same motion using three motion graphs: the acceleration graph, the velocity graph, and the position graph. First, the acceleration graph. Since acceleration is constant in this type of motion, the graph is just a horizontal line at a fixed value. And remember, the area under this graph, the shaded region between the curve and the time axis, represents the change in velocity. Next, the velocity graph. This graph gives us the most useful information. Since velocity is increasing at a constant rate, the graph is a straight, upward sloping line. The slope of this line is equal to acceleration. That makes sense if you think about the definition of acceleration. It is the rate of change of velocity. And once again, the area under the velocity time graph represents displacement. This is a really important connection. Velocity versus time gives us displacement. Finally, the position graph. Even though we cannot draw it exactly, we know its general shape. As time goes on, the object's position moves farther and farther away from the starting point. So the curve must be parabolic. And do not forget, the slope of the tangent line to this curve at any point gives you the instantaneous velocity at that moment or at that position. So these three graphs together not only describe constant acceleration motion, but they also allow us to identify it whenever such graphs are given. Now let us summarize the kinematic equations, which are the mathematical tools we use to calculate velocity, displacement, and position. At first glance, these equations may look complicated, but actually, you already know everything about them. We are just rewriting the same ideas in math form. To make things easier, we usually assume the motion starts at time t equals 0. That way, all time intervals can just be written as t. Here is the summary. Acceleration is the change in velocity divided by the change in time. Since this is constant acceleration, it always has the same value. Velocity at any moment is equal to the initial velocity plus the change in velocity, and that change in velocity is acceleration times time. So velocity equals initial velocity plus acceleration times time. Displacement at any given time is equal to the area under the velocity time graph. If we break that shaded region into a rectangle and a triangle, add their areas, and then simplify, we get displacement equals initial velocity times time plus 1/2 acceleration times time squared. Finally, position equals the initial position plus displacement. In other words, position equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. If the motion starts at the origin, then the initial position is 0. And if the object starts from rest, then the initial velocity is 0. In that case, the formula simplifies to position equals 1/2 acceleration times time squared. If we combine the velocity equation and position equation and eliminate time parameter, then we can get another formula, so-called velocity-displacement relationship. This equation is very useful because it connects velocity and displacement directly without involving time. So these are the main equations we use for constant acceleration motion. That was a pretty detailed review of constant acceleration motion. And you might be thinking, wow, that alone feels like a whole lecture. But do not worry, this foundation is really important, because now free fall will be much easier to understand. As I mentioned before, free fall is nothing new. It is just constant acceleration motion in the vertical direction. So let us take all the ideas, graphs, and equations we just reviewed and apply them vertically. Free fall motion is the kind of motion where an object is accelerated because of Earth's pull, in other words, gravity. Just like in the picture, imagine letting go of an object in the air and watching it fall straight down. That's exactly the motion we are talking about. Since we are talking about a natural falling motion, we'll assume there's no extra push and no air resistance. Because Earth pulls the object downward, the motion is accelerated in the vertical direction. If the constant acceleration motion we studied before was horizontal, moving side to side, then free fall is that same type of motion, but in the vertical direction. As shown in a motion diagram, free fall is an accelerated motion where the speed increases as time passes. That's why its position graph looks like a parabola, as you can see in the figure. One thing to be careful about is that because the motion is downward, the position graph usually appears in the negative direction. Of course, as I'll explain later, the direction of the position can change depending on how we choose the origin and how we define the positive direction for the motion. In fact, this is the very first step in solving real problems, deciding where the origin is and what counts as the positive direction. We'll organize and practice this in detail later in today's lesson. For now, just think of this as a preview. We call this process deciding the coordinate system. So just remember the title for now. Now, coming back to free fall, there's really nothing new here. Free fall motion is just the same one-dimensional constant acceleration motion we studied earlier. The only difference is that the direction is vertical instead of horizontal, so all you need to practice is setting up problems and thinking in the vertical direction. All right, then let's look at the key point of free fall, the acceleration due to gravity. So, free fall motion is constant acceleration motion caused by Earth's gravity pulling on an object. But how much is that acceleration? For every object on Earth, regardless of its mass, the acceleration is 9.8 meters per second squared. This is what you've probably heard about from Galileo Galilei's famous Leaning Tower of Pisa experiment, where objects of different masses supposedly fall with the same acceleration and hit the ground at the same time. But you might also know that this wasn't actually a real experiment. It was a thought experiment. Anyway, let's focus on the fact that a falling object always experiences this same acceleration. The acceleration due to gravity is a vector quantity. It always has the same magnitude, 9.8 meters per second squared, and its direction is downward. We can write this in two ways, either by saying its magnitude and direction separately, or by writing it as minus 9.8 meters per second squared using a negative sign. The negative sign here means we defined upward as the positive direction of the motion, but if instead we had chosen downward as the positive direction, then the acceleration would be written as plus 9.8 meters per second squared. In other words, the sign of acceleration depends entirely on how you define the positive direction of motion. So it's a good idea to decide once and for all which positive direction you'll use when solving free fall problems, and then stick with it consistently. That's what we meant earlier when we talked about choosing a coordinate system. In the end, when you solve problems, the signs in your equations will depend on this choice. That's why simply memorizing formulas isn't enough. You really need to understand what's happening. Okay, so now let's organize the kinematic formulas for free fall motion. Just like in horizontal motion, where we usually take the rightward direction as positive, in vertical free fall we usually take the upward direction as positive. In this case, the acceleration of the falling object is g. Other than that, all of the kinematic formulas are exactly the same as the ones we studied before. The only change is that the acceleration is replaced with g. As you can see, the formulas show the velocity and position at any time, as well as the relationship between velocity and displacement without time parameter. Again, the only difference is that acceleration is written as g. And since we are talking about vertical motion, the position variable is written as y instead of x. That's just because in a standard coordinate system, the vertical axis is labeled y. It's not a big deal. Also, just like before, if the initial velocity is 0 or if the initial position is 0, then the formulas simplify into shorter forms as shown. If we draw the acceleration graph, the velocity graph, and the position graph for free fall motion, they look like this. Remember, since we defined the positive direction as upward, the acceleration graph shows a straight line at minus 9.8 meters per second squared, a negative value. The velocity graph shows a straight line sloping downward because the speed is increasing in the negative, downward direction. And the position graph is a parabola curving downward, showing the object moving farther and farther in the negative direction. So, that's the explanation of free fall using motion graphs and kinematic formulas. Not much is actually new here, right? Now, let's try thinking about some problems involving constant acceleration motion. Let's now summarize the types of free fall problems you'll usually see. Most of them can be grouped into three cases, as shown in the figure. The first type is what we usually call free fall. A person drops an object from rest starting from a certain height. Since the object starts at rest, the initial velocity is 0, and then as it falls, it speeds up due to constant acceleration. The second and third types are actually the same kind. A person throws an object upward. The object moves upward, slows down, stops at its highest point, and then reverses direction and falls back downward, even though it may sound a little strange to call the upward motion free fall. From a physics point of view, the same laws of motion and the same gravitational acceleration apply. That's why we still consider the upward motion as part of free fall. The reason we separate the second and third cases in the diagram is because, when solving problems, you need to be careful depending on how you set your origin and which direction you choose as positive. The interesting part is that all three types of free fall motion can be solved using the same three kinematic formulas we studied earlier. At first, it might feel strange that different-looking motions can all be solved with the same formulas, but for us, that's actually good news. It means you need to memorize only 3 formulas. As long as you understand the problem correctly and apply the formulas carefully, you'll be fine. So, to summarize, the 3 formulas for vertical constant acceleration motion free fall look just like the formulas we studied before for horizontal motion. The only difference is that instead of using acceleration A, we now plug in G. Also, notice that we use Y for position here because vertical motion is measured along the y-axis. That's not especially important, it's just standard notation. But here's something you do need to be careful about. The acceleration has a negative sign. Why negative? We'll explain this clearly when we go through the actual problem-solving process on the next page. Now, let's go over the 7 steps for solving a typical one-dimensional constant acceleration motion problem, like free fall. This approach can be applied to any constant acceleration motion problem you'll encounter in the future. It might sound like a long explanation, but the core idea is actually really simple. Alright, let's take a look. First, we need to read the problem carefully and make sure we understand it. Is the ball being thrown upward or dropped downward? How fast is it thrown? How high is the starting position? These are questions of comprehension, and you could even say it's the most important step, so-called step 0. I don't think this is something I can fully explain here. Anyway, let's assume that we've read the problem carefully and understand it, and start from there. To solve the problem mathematically, we first need to decide on the origin and the direction of motion. These are the first and second steps. Let's take the example shown on the right. A person throws an object upward from a high place, and the object goes up, stops, and then falls back down. The first step, choosing the origin, is about deciding the starting position of the object's motion. As I explained way back earlier, you can choose the origin wherever you want for your analysis. It's completely up to how you interpret the motion. Generally, people often choose the point where the object's motion starts as the origin. In the example on the right, we'll take the point where the object is released, marked by 2 red circles, as the origin. That's the first step. The second step is deciding the direction of motion. As I mentioned before, one-dimensional motion only moves left, right, or up, down. So it's convenient to set one direction as positive and the other as negative when you write the equations. For horizontal motion, we usually take the positive direction along the x-axis, that is, to the right. For free fall motion, we generally take the upward direction along the y-axis as the positive direction for the object's motion. Of course, you could choose downward as positive as long as you carefully handle the signs. But for most free fall problems, taking the upward direction as positive is standard. If you choose the upward direction as positive, all kinematic formulas look as shown on the previous page, with the acceleration A equal to g. That's the second step. Now, once you've decided on the origin and the positive direction of motion, the third step is to express various physical quantities, like position, velocity, and acceleration, using appropriate variables. Unless there's a special case, the usual way we've been using these variables works fine. The fourth step is to write down the values of the known quantities from the problem using those variables. Depending on the problem, it might give you the initial velocity, the initial position, the time to reach a certain point, or the final velocity. Basically, in this fourth step, you're making a list of what you know among all the physical quantities that describe the motion. Next, the fifth step is to figure out what quantity the problem is asking for. In other words, this is the stage where you make sure you clearly understand what you need to find. Up to this point, you're basically preparing the problem to solve it. If you've understood the problem correctly and expressed it in a suitable form with variables, you're almost done with the problem already. The sixth step is to apply the 3 kinematic formulas we know. In other words, use the equations to do the calculations. You take the variables you know and the variables you want to find, choose the right formula, and calculate. It's easy to think that solving a problem is mainly about calculation, but the real key is in these previous steps. The final step is to think about whether the result makes sense. Most physics problems are based on realistic quantities, so if the problem describes a real situation, your answer should also be reasonable. For example, if someone throws a ball and your calculation shows it flew hundreds of kilometers, you clearly did something wrong somewhere. This kind of verification is really helpful when solving problems. So that's a summary of the steps for solving one-dimensional constant acceleration motion problems. You need to practice these steps repeatedly so you can apply them naturally. In the next chapter, we'll try a few simple practice problems. Next, here's a very typical free fall problem. A person throws a rock upward from a 20-meter cliff at a speed of 13 meters per second, and the rock goes up and then falls back down. When you see a problem like this, it's really helpful to first understand it and visualize the situation in your mind, like in the diagram on the right. In this scenario, the problem asks you to calculate the rock's position and velocity after 2 seconds, and also to find the rock's velocity when it has fallen 5.1 meters below the standing position. Alright, let's apply the steps I explained earlier to solve this problem. The first step is to decide on the origin for solving the problem. Generally, we take the starting point of the object's motion as the origin, so we'll do the same here. The two red circles in the diagram show the initial position. The second step is to decide the positive direction of the motion. Generally, we take the positive direction along the y-axis, meaning upward, so we'll take the upward direction as positive for this motion as well. The red arrow pointing upward in the diagram shows the positive direction of motion. Now, the third step is to express the various physical quantities of the motion with suitable variables. Since we are not using any special variable names, we'll assign the variable names when we apply the fourth step. The fourth step is to represent the quantities we know as values of those variables. The given quantities in the problem are the height of a cliff, 20 meters, and the initial velocity of a rock, 13 meters per second. Here, the important thing is the direction of the velocity, meaning the sign. Since we chose upward as the positive direction, the initial velocity is plus 13 meters per second. Be careful about the sign of the velocity. Also, even though it's not mentioned in the problem, for free fall motion, the acceleration has a magnitude of 9.8 meters per second squared and points downward, so the sign is negative. Pay attention to why the initial velocity is plus and the acceleration is minus. If you think about it carefully a few times, you'll get used to it quickly. Next, the fifth step is to check what values we need to find. The problem asks for the position and velocity after 2 seconds, so the variables we want are the final position and final velocity after 2 seconds. After 2 seconds, the motion might not be completely finished, but our focus is only on the time range from 0 to 2 seconds, so we'll call them the final position and final velocity for convenience. More precisely, they're the position and velocity at 2 seconds. Now, the sixth step is the actual calculation. First, to find the position after 2 seconds, the final position, we use the formula shown here. By plugging in the values we know, we can calculate the final position we want. One thing to note here is that, in free fall motion, the gravitational acceleration is minus 9.8 meters per second squared as a vector considering the direction, but in the kinematic formulas we memorize, the sign has already been accounted for, so we only need to plug in the magnitude, 9.8 meters per second squared. Let's check the final result we get, 6.4 meters. Since the initial position is the standing position, a 6.4 meter displacement in the positive direction could be somewhere along the upward path or the downward path. We don't know exactly where yet, but it seems like a reasonable value. Next, the problem asks for the final velocity after 2 seconds. We can calculate it as the initial velocity plus the change in velocity, plugging in the known values. Again, note that we only consider the magnitude of gravitational acceleration in this calculation. Let's check the final velocity after 2 seconds. The calculation gives a final velocity of minus 6.6 meters per second, so the rock is moving in the negative direction, meaning downward. Earlier, when we saw the rock was at 6.4 meters, we weren't sure if it was going up or down, but now by calculating its velocity, we see it's on the way down. You see what I mean? That's why the sign is so important. It really helps describe the motion of the object. And the next problem asks for the velocity when the rock has fallen 5.1 meters below the starting position. This is a different time interval, so the variable we want to find is again the final velocity for that time interval. It's helpful to think of it as a separate final velocity for a different time span from the previous final velocity. Since we don't have time information, we'll use the third kinematic formula that relates velocity and displacement. By substituting the known values, we get the square of the final velocity as 268.96. Taking the square root gives two possible values, 16.4 meters per second. Since the rock is below the cliff, the velocity must be negative, so the final answer is minus 16.4 meters per second. Again, this shows how important the sign is for interpreting the motion. Also, when applying the velocity displacement formula, pay careful attention to the displacement value. Displacement is defined as final position minus initial position. The final position is 5.1 meters below the cliff, so minus 5.1 meters, and the initial position is the origin, 0 meters. Thus, the displacement is minus 5.1 meters. Because we set up our coordinate system this way, make sure you handle the signs correctly in your calculations. The problem doesn't ask this, but let's try something interesting. Let's calculate the velocity when the rock comes back to my position after being thrown upward. Again, since we don't have time information, we can use the velocity displacement formula. Thinking about the displacement in this case, the final position is back at me, 0 meters, and the starting position is also 0 meters, so the displacement is actually 0. Remember how we calculated distance and displacement when we ran around the track and returned to the starting point? Since the displacement is 0, the final velocity when the rock comes back to my position is minus 13 meters per second. The interesting thing is that in free fall motion, when you throw a ball upward from your position and it comes back to you, the speed has the same magnitude as the initial speed, but the direction is reversed. It makes sense intuitively, and the calculation confirms it exactly. So everyone, make sure to practice calculating carefully, paying attention to the variables that describe motion and the signs. Finally, let's briefly look at a free fall problem in 2 stages. This type of problem is often considered difficult on exams, and it also connects to the topic of forces that we'll cover in the next chapter. Here, I'll just explain the basic idea briefly. We'll go through the full problem solving in another lecture. Typically, these problems involve insects or animals that gather energy by crouching and then push off the ground to jump. We can interpret these motions using the constant acceleration motion and free fall motion concepts we've learned so far. We can divide this into 2 main stages. The diagram shows the example of a frog. The first stage is the frog crouching on the ground and just before it pushes off, and the second stage is the free fall motion, where it leaps up and then falls back down. The stage where the frog crouches and then extends its body is one instance of constant acceleration motion. Then, from the moment it pushes off the ground and jumps up until it falls back down, that's free fall motion, which we can calculate using the same ideas we used in the previous chapter. We'll go over the detailed problem solving in the next lecture. So far, we've studied the theory and some simple examples of vertical one-dimensional constant acceleration motion, that is, free fall motion. It may seem a bit complicated, but if you understand the explanation and practice with problems, it will make sense. From the next chapter, we'll apply a new physical concept, force, which is the source of the motion, along with the relationships of the motion we've learned so far. This will allow us to analyze the motion of objects more accurately. That's all for today's lecture. Great job, everyone, and thank you for sticking with it for such a long session. You better keep learning about motion by watching short videos, even if it's just a little at a time. See you next lecture.